In the previous video, we found that the short-run cost relationships for an individual firm, once we factored in the law of variable proportions, looks like this. At low levels of output, the variable cost curve is likely to rise at a decreasing rate as output increases due to increasing marginal returns resulting from specialization. Here you can see that the variable cost curve is rising at a decreasing rate because marginal returns are increasing as a result of the benefits of specialization. After some point, however, the benefits of specialization are eclipsed by the inevitable law of diminishing marginal returns and its corollary, the law of increasing marginal cost. Those rising marginal costs are causing the variable cost function to increase at an increasing rate. The curvature of the variable cost function also causes the total cost function to be similarly shaped. In fact, the total cost function is vertically parallel to the variable cost function. But when modeling the behavior of the individual firm, we're going to find it more convenient to use the average or per unit cost curves and the marginal cost curve rather than these total cost curves. We'll derive the average cost curves by constructing a table, filling in values that reflect the characteristics of these total cost curves. Then we'll compute the relevant variables and observe the characteristics of those functions. Let's start with the independent variable quantity. As you can see here, the firm's maximum production capacity is 10 units of output per period. Let's call a period a day. The firm can produce anywhere between 0 units and 10 units of output per day, but cannot exceed that limit in the short run. Here are the same fixed costs that we used in the previous video. If we plotted those values, as you already know, the fixed cost function would look like this. Here are the values for the variable costs that we also used in the previous video. But if we use those values, the variable cost function would look like this. But we've already concluded that the variable cost function should look like this because of the law of variable proportions. So, what will these values for a variable cost function have to look like in order to produce the function that you see here? We know that when output is 0, variable costs are also 0. But then variable costs must begin increasing at a decreasing rate as output increases. This, of course, is the phenomenon we called increasing marginal returns and its equivalent, decreasing marginal costs. Let's take a look at these values. You can see variable costs are going up as output increases from 0 to 6 units, but at a decreasing rate. That is, marginal costs are going down. But after the 6th unit of output, the variable cost function starts rising at an increasing rate. That is, marginal costs begin to rise. As output increases from 6 to 7, variable cost increases by $7. As output increases from 7 to 8, variable cost increases by $13, then $18, then $27. The law of increasing marginal cost is setting in because marginal returns at this point are diminishing. In the area shaded in green, we can see that the variable cost function is rising at a decreasing rate because marginal costs are decreasing. In the area shaded in red, the variable cost function is rising at an increasing rate because marginal costs are increasing. In the area shaded in red, Now, if we add fixed costs and variable costs, the total cost function will look like this. As you already know, the total cost function is vertically parallel to the variable cost function. We have here a set of values in the table that reflects the shape of the total cost functions, the total cost, the total variable cost, and the total fixed cost. We can now derive the average or per unit values that we'll be using in our models. But before we get into the average or per unit costs, let's derive marginal costs. As you can see, marginal costs can be computed either as the incremental change in total costs or the incremental change in variable costs. Now, let's derive average fixed costs, which is, of course, total fixed cost divided by quantity. There's average fixed cost. Take just a second to confirm that those values are correct. And average variable costs can be computed in the same way. Average total costs can be computed either by dividing total costs by Q or by simply adding average variable costs and average fixed costs. If we were to take the time to plot all of these values on this graph, here's what the functions would look like relative to one another. Let's consider some salient features about these relationships. First, note that the ATC curve starts at 120 at 1 unit of output and continues to fall up until the 9th unit of output, but then begins to rise. The AVC curve has a similar shape, but bottoms out at about the 7th unit of output. The marginal cost curve bottoms out even earlier, in this case at about the 6th unit of output. It is also the case where the MC curve intersects both the AVC and the ATC curves at their minimum points, points B and C respectively, on the graph. This is a mathematical relationship. If the marginal lies below the average, it pulls the average down. If the marginal lies above the average, it pulls the average up. Thus, the marginal cost curve must cut the average cost curves at their minimum points. The AFC curve is not even plotted on this graph, yet the information is still there. You can see that by the difference between the AVC and the ATC curves. Recall that the difference between the ATC and the AVC is the AFC. As you can see in the red shaded area, that if we were to plot the AFC, it would continuously fall. The curve would get closer and closer to the zero axis, although it would never actually touch it. The continuously diminishing AFC can be seen by the AVC and the ATC curves getting closer and closer together. Here's what the short-run cost relationships would look like if we quickly sketched it out on the blackboard.